Today's lesson is on specific heat and calorimetry. In addition to your notes handout, you'll need your calculator today because we'll be doing some math problems, not tricky math problems, only one equation that we'll be using for our math problems today, but we will need a calculator for it. So let's get started. So what is heat? We've seen this term before. Okay, heat, we use the symbol Q in chemistry to represent heat. Heat is energy transferred between two samples of matter due to a difference in temperature. And heat is always transferred from hot to cold. We talked about in our intro lesson to energy that heat and temperature are not the same thing. Temperature is just a measure of the average kinetic energy of the particles in a sample of matter. But heat is the energy that's actually transferred between two samples of matter due to a difference in temperature. Yes, always transferring from hot to cold. Now, I can use our temperature to help me measure heat. I can look at a sample of matter that heat has transferred from or away from, or transferred from or to, and I can measure the change in that temperature of that sample of matter to figure out what that heat was. Last lesson, we talked about this term called enthalpy, right? Enthalpy is H. Enthalpy for chemical reactions let me know what the energy content is within a substance, right? Now the delta H here, delta H stands for the change in enthalpy throughout the course of a reaction, right? We want to know what the energy content of the reactants and the products and how they are different. We use these terms endothermic and exothermic, right? We know that if a reaction releases heat, we would call it a negative delta H, and it would be an exothermic reaction, right? And if a reaction absorbs heat, we would have a positive delta H, and we would call that an endothermic reaction. Well, these reactions are involving a energy transfer, right? Either from the surroundings into the system or from the systems to the surroundings. So we can also represent these chemical reactions with heat transfer as well, which is why you'll see underneath my delta H, I have a Q. I've also put signs there. Conveniently enough, the sign for delta H will match the sign for Q. So we can also make this statement or assume that a negative Q means that energy or heat is released, and a positive Q means that energy or heat is absorbed, which is really cool and convenient, which means my brain does not have to switch around too many things. Negative means release, positive means absorb. Okay, so what is the deal? How can we measure heat? Y'all, the units for heat are joules. We've seen joules before. Or look at this, calories. You're like, oh my gosh, like the calories from the nutrition labels. Yes, oh my gosh, yes. Joules is the technical SI, the science unit for heat. But calories is another one that scientists can use. It's the more well-known, obviously, unit for heat. And technically, it's the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. And now I'm going to call these calories because we're used to actually seeing something called kilocalories on our food labels, okay? Or a capital C calorie. You're like, that is so super annoying. I kind of agree. If you go outside of the United States on their nutrition labels, they will actually have kilocalories written in there. Here in the United States, we've just decided to call kilocalories a capital C calorie. So the main thing here is that little c calorie is not the same thing as big C calorie, okay? So 1 calorie, big C calorie, or kilocal is equal to 1,000 calories. And y'all, 1 calorie is equal to 4.184 joules. So here's a conversion or equality that would allow for me to convert from joules to calories or calories to joules. Okay, so that's the units that I measure heat in. Here's an equation that I can use to calculate the heat that's transferred. Q is equal to mCp delta T. I like to call this Q is equal MCAT. Okay, the MCAT is a test that people trying to get into medical school have to take. I have heard it's very difficult. I look at that and just visually it looks like MCAT to me. So that's how I remember what this equation is. Regardless, you'll always get the equation from me to where you don't have to have it memorized, but if you hear me say Q equals MCAT, I'm just talking about this heat equation. So what do all these letters of the alphabet mean? Q, we've talked about Q. Q is just heat. It is energy lost or gained. As we referenced from the previous slides, we know that if Q is negative, it will be a release of heat, an exothermic process. And if Q is positive, it's going to be an absorption of heat, an endothermic process. But the units for Q we talked about are joules. M is mass, the mass of the substance that I'm looking for, whether the absorption or the release of energy has occurred on. C sub P, this is a new term probably. That stands for specific heat. Now look at the units on this guy. Joules per grams degrees Celsius. You're like, oh, we will unpack how we get that here in a second. And then last thing I want to talk about here is delta T. We have seen these delta symbols. Delta always means a change. So delta T stands for the difference in the initial and final temperature in degrees Celsius, or the change in the temperature that has occurred from that heat transfer from its initial state to its final state. Now to calculate delta T, it's a quick little subtraction. I take the final temperature after the energy transfer minus the initial temperature before the energy transfer. The way I remember it's always final minus initial is that F comes before I in the alphabet. So we're alphabetical. We love that. It also kind of follows the same trend of our delta H equals products minus reactants that we talked about last time, where products minus reactants is alphabetical. But also the products are the final thing from a chemical reaction, and then the reactants are the initial thing in a chemical reaction. So for all of our delta equations, whether it's delta H enthalpy or delta T here, it's the last ending final thing minus the first initial starting thing, which is good. And they're alphabetical, which we love that. Okay, so let's talk about this CP nonsense here. Specific heat. Y'all, it is the amount, that y'all are not ready for this. It is the amount of energy needed to raise the temperature of 1 gram of any substance up by 1 degree Celsius. You're like, what is even happening here? I have to kind of break it down in my dumb brain and think, okay, let's remember this statement. Okay, the specific heat of water is 4.184 joules per grams degrees Celsius. By definition, and by looking at this number, this means that it takes 4.184 joules to raise the temperature of 1 gram of water up by 1 degrees Celsius. So now I can kind of see how those units of specific heat kind of give me the definition. It's how much joules are required to heat up a gram by 1 degree Celsius. So that's why you see those units on the bottom. Now, looking at here, a lot of people will use specific heat with kilograms as opposed to grams, which is why down here on this picture example, you see the joules value up by a factor of 1,000 because I'm representing kilojoules. If it were doing for grams, that number for water is 4.184, which is what we will be using standard. But here that just means, okay, I have to, boom, shoot that much heat energy into that sample of water to move its temperature by 28 degrees to 29, okay? But the units are joules per grams degrees Celsius. You're like, well, then why is this symbol for specific heat, which is a S for specific and an H for heat? Why is the symbol CP? I agree, that is nuts. The reason why I had to look this up, the reason why it's CP is that it is usually measured under constant pressure. So there you go. I guess we love that. Okay. But here's the key thing about specific heat. The specific heat of a substance is unique to the substance. That means the specific heat of water, which we said was 4.184 joules per grams degrees Celsius, is completely separate and unique to water. The specific heat for iron is going to be something different. The specific heat for oil is going to be something different. The specific heat for hydrogen is going to be something different. It is an intensive property of matter, meaning it does not matter how much or how little of something I have. It just means whatever that sample is, that is what specific heat is representing. So water has 4.184 joules per grams degrees Celsius as its specific heat. Iron specific heat is always 0.450 joules per grams degrees Celsius. Why are those numbers different, and what does it mean? What does it mean that water specific heat is higher, and why is iron specific heat lower? What does that mean? How does that affect that substance ability to absorb or release energy? Well, let's watch a video and find out.
Okay, Year 11, today we are going to learn about what specific heat capacity is, and hopefully by the end of this video you'll have a better understanding of what that phrase means. I want you to imagine you're at the beach, and here we've got the sun, and the sun is giving the same amount of energy to both the sand and the water. But even though it's the same amount of energy, you'll notice that the sand actually heats up a lot quicker and to a higher temperature than what the water does. So even though the same amount of energy, the sand will have a larger rise in temperature than the water. This is because when we put the same amount of heat into some materials, it actually gives a bigger temperature rise in one than it might in the other. So let's use another example of this. If we have two beakers and we put the same amount of water in one as an amount of oil in the other, let's say 1 kilogram of each, water and oil, and we heat both of them for the same amount of time at the same temperature, what we would actually find in this experiment is that even though we've got identical volumes of water and oil, and they're both heated at the same amount of time, so for 1 minute, the oil will actually heat up to 60 degrees while the water will only heat to 30. So the same amount of heat produces twice the temperature rise in oil than it does in the water. To make the water reach the same temperature as the oil, we would have to add twice the amount of heat to the water. This means that water has twice the capacity to absorb and store heat energy as the oil. So we say that water has a higher heat capacity than oil.
So yes, specific heat is the amount of heat energy in joules needed to raise 1 gram of a substance up by 1 degrees Celsius in temperature. Water, like the video said, has a super high specific heat, right? It was a much higher specific heat than that oil sample. That means it takes a lot more energy to get it to change its temperature. We're going to do more on this in future units. But looking at this here, a few samples, water's way up here with that really high specific heat, right? And then down here I have some metals. Like copper has a specific heat of 0.385 joules per grams degrees Celsius. And magnesium has a specific heat of 1.02 joules per grams degrees Celsius. Okay, that means that not that much energy is required to raise their temperatures up, right? Versus water is going to take a little bit more time and energy input for it to show a temperature change. If you think about it, if you put a pot of water on a stove top and you wait for the water to boil, we know that pot, that metal pot, gets hot real quick. That's because it's got a low specific heat. Don't take much energy for it to heat up. But the water inside of the pot, it takes much longer for you to notice a change in temperature at all, and a long time for it to get its temperature up to a boiling. Okay, so just think about what types of things get hot quickly, and those are your guys who have really low specific heats. Okay, we'll talk about the important part of water's high specific heat and how that is very important to life here on Earth in future units, like I said. Okay, now we're going to bounce down, I think, to the document camera, and we're going to do some problems with this Q equals MCAT equation, which I'm really excited about. Okay, so you will need your calculator. I'm going to see if a zoom in is too aggressive. I think that's fine. Oh yeah, that's going to be super fine. Okay, so the question says, how much energy is required to heat an iron nail with a mass of 7.0 grams from 25 degrees Celsius until it reaches 750 degrees Celsius. And then the specific heat of iron I gave you is 0.448 joules per grams degrees Celsius. There's lots more numbers here in these problems. That is okay. We can circle these numbers, and by looking at their units, we can be like, oh, I know what that is. That could be an M or a CP or a Q. So let's see. The first thing I see is it says, it even tells you, is a mass of 7.0 grams. Even if they didn't say a mass, if they said an iron nail that is, or a 7.0 gram iron nail, we see grams and we were like, yeah, that is a unit for a mass value. So I'm going to write an M right above him. From 25 degrees Celsius, oh, we know that's a temperature. That's not scary. So that's a temperature until it reaches 750 degrees Celsius. That's a temperature. Okay, well, which is which? We know we have a final temperature and an initial temperature because my equation tells me I have a delta T, which is final minus initial. Well, it says it went from 25 degrees Celsius until it got to 750 degrees Celsius. So that means that 25 is my initial, and then this 750 is my final. Okay, and then the last number that they gave me here is they gave me the CP. If I saw the units, joules per grams degrees Celsius, those are the units for a specific heat, okay? So I can still identify all of these guys based on units. Awesome. So now what are they asking me to solve for? How much energy? Energy or heat is the symbol for Q. So I'm solving for Q. Let's go ahead and state our equation. Q is equal to M CP delta T. We have the M, we have the CP, we have the delta T. Okay, you have two options for how you want to implement delta T in here because it is a subtraction step. I'm going to show you the two options, but let's go ahead and start putting in some of these masses and stuff like that. So I wrote my equation down. Now I'm ready for the substitution step. So my mass is 7.0 grams. Right, and my specific heat is, let's see, it was 0.448 joules per grams degrees Celsius, right? And then my delta T, you can either up here off to the top, delta T is equal to your final minus your initial. You can show that math up here, right? And I'm actually going to put that decimal because there is a decimal in this guy. And do this math first before you plug it in, okay? And I'm going to show that on my calculator because it's going to have a very important point. So I have 750 minus 25. So the delta T is 725 degrees Celsius. 725 degrees Celsius. Okay, so I can plug that in as is. Or if you were like, I don't want to have to write all that work, I totally agree. You can, in here, in parentheses, you can do your finest minus initial in there. Meaning you can go like this. 750 degrees Celsius minus 25 degrees Celsius. Okay, that is easier for me, but if you choose to do this way, you're going to have to be on sig fig alert. What this means is my sig figs and roundings are kind of following an order of operations, which mean we first address anything that's a subtraction or an addition and grab on whatever the result of a subtraction or addition rounding solution is, and then that gets implemented into the rest of the multiplication process as then you address the sig figs of it all. You're like, what did she even mean? Well, if we subtract things or add things, we are looking at place value, maintaining the place value of the least precise number going into it. Well, it looks like everybody in here, the least precise value is in the ones place on that one because they're telling you with that decimal that that 0 is significant. So that's the least one. And then here, the 25 also falls into the ones place. So that means my answer from any subtraction or addition problem has got to be there in the ones place. Now, this gives me a number with how many total sig figs? 3 sig figs. Which means I've got a 3 sig fig situation in here to where when I get to my multiply, I've got to make sure that I know that that is 3 sig figs. Okay, so this is weird. What I like to do is, even if I like to do it this way, I kind of like to real math it out in my head or on the calculator, and I like to write out what the result of that subtraction is because that's the guide that I'm going to use for sig figs. Okay, the next thing I haven't even touched my calculator, but I'm talking a lot about sig figs. The next thing I want to talk about is the specific heat is a kind of, if you want to think about it, a constant. It is a constant specific to what the substance is. So that will be a different number each time depending on what substance I'm giving you. But we're not going to look at sig figs for that guy. It would be considered infinitely significant. So don't look at CP for sig figs. Okay, a lot of talking. So now I'm just basically multiplying 3 numbers together. 7.0, let's get our calculator out, make it happen. 7.0 times 0.448 times, what is it, 725, right? Okay, so we get this number, very excited about that. I'm going to write that number down just so we have it on our paper and then we can, swirl around and do some rounding, hopefully. So what we get is 2273.6. And I'm not even going to write the units yet. I'm going to wait for the rounding of it all. Okay, the sig figs of it all. We said that this subtraction step is the sig fig we're going to be using for this. So we have a 3 sig fig situation coming from my temperature. I ignore the sig figs from my specific heat, but oh, yo, how many sig figs do I have here for my mass? I have 2 sig figs. So the rule is when I multiply stuff together is I've got to round my answer to the value's least significant number, which value has the least number of significant figures, and that is a 2, which means on my answer here I've got to grab that first 2, I've got to grab that second 2, I have to round that second 2 up to a 3 because the guy behind him is a 5 or greater. So that means my answer is not 23. That original 2 was in the thousands place, and that one was in the hundreds place. So to keep them in their place, I have to add zeros at the end. Do not put a decimal, or else those zeros would be also considered significant. They are not. Okay, so you're like, oh gosh, now what units have I need to do here? Well, the units, you can either memorize what everybody's units are in here, or the fact that I made you write the units in here is you can kind of be like, oh, the units have just spilled out onto me. If I have a grams here and I'm dividing it by a grams from this specific heat value, the grams disappear. Also, if I have a degree Celsius here and I'm dividing it by degrees Celsius, guess what? Degrees Celsius go away. Grams and degrees Celsius, poof, they go away because they cancel each other out. So my only remaining unit that I would get from this calculation is joules, which is cool, right? I could also ask maybe an extension question if I wanted to be like, how many kilojoules would that be? Okay, how many kilojoules? Well, going from joules to kilojoules is just a factor of a 1,000, right? So I would take where the decimal originally sits and bump it back 3 places to where that this would be 2.3 kilojoules, which is really, really, really cool. The next thing I want to address, we talked about what it means when Q is negative and Q is positive. I have a positive number here. So that means that energy was absorbed, okay? So absorbed because a positive Q, yes? Okay, and I can even go back to the problem and say, well, does the problem in the way they're describing this process, does that make sense that the iron is absorbing heat? Let's see. Well, well, I'm heating up a piece of iron from a cooler temperature to a hotter temperature. So to get somebody to heat up, yeah, that iron, that makes sense that he's absorbing heat energy to heat himself up. That was our first example. The sig figs of it all are a little bit sneaky. Sorry, temperature change. That is super annoying. We just have to kind of be aware of that. Okay. Next problem, it says when a 50-gram piece of nickel, I'm going to go ahead and circle this 50 grams. I see grams. It is a mass for me. Of nickel absorbs 350 joules. Oh, that joules is giving something away. Who is the units for joules, or who has the units for joules? That is Q. The temperature of the nickel changes from 20 degrees Celsius to 36 degrees Celsius. So if it's changing from 20, that's my initial temperature, to 36, that's my final temperature, right? What is the specific heat of the nickel? So I'm solving for CP. Okay, so state my equation down. And that's another bonus about writing all of my symbols above this, is that I actually see Q's and M's and CP's, and I'm like, oh, I know what equation to use. It is Q equals MCAT. So then you can blast that equation down. Write it down so you know what you're telling me that you know what you're doing to solve it. And I'm going to have to rearrange this equation to solve for CP. You can either substitute everything in as is, as you're seeing it in that order, or if you're like me, I like to rearrange it first when I just am dealing with letters of the alphabet, as opposed to rearrange things later when now I've got numbers and I will probably get lost. So that means to get CP by himself, I would have to get his sneaky buddies of mass and delta T away from him by dividing both sides by mass and delta T, which means CP would be equal to Q divided by those sneaky original buddies, mass and delta T. Okay, so now I'm ready to plug in some stuff, right? So I got Q. My Q is 350. And yes, that decimal behind that 0 is important, right? Joules. And then my mass, we said, was 50.0 grams. Yes. And then my temperature change, just so I don't have to do too much writing, I'm going to write it like I did here, just a final minus initial embedded all in there. And then in my calculator, I will, of course, do that subtraction and check out the sig fig. So I will make sure I know how to round correctly. So I went from my final temperature is 36.0 degrees Celsius minus my initial temperature of 20.0 degrees Celsius. Okay. All right, so let's tackle that delta T first. I want to see what we got going on here. So we have 36. We can't see. There we go. 36 minus 20. Okay, so yes, I know I get 16, but remember we talked about subtraction or addition. I'm looking at that place value. So yeah, it's 16 perfectly, but according to that, that means I need to have a 16.0. I need to have somebody in that tenths place. So the kind of result of this, if we want to jot it down, is 16.0. Now that's important because that number is showing me 3 sig figs, which I will have to be aware of when it comes to the rounding. And I'm not going to require for you to show this value. You can even totally type this into your calculator, just boom, 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 and then that all in parentheses. But if you're not kind of keeping awareness of how many sig figs that subtraction step is, you may get a little bit lost. I promise I'll stop talking so much in depth about that, but I just wanted to establish that to make sure that we're all good. So that means when I grab my calculator, I'm ready for this step. I've got 350 divided by my mass was 50, right? And then I'm also dividing that by 16. So get this, that's super amazing. First of all, how many sig figs do I need to round to? We only look at everything besides specific heat. Specific heat is not even in here. So I've got to look at everybody. So this has got 3 sig figs. This has got 3 sig figs. And this, my delta T, has 3 sig figs. Okay, everybody got 3 sig figs. That is great and convenient for me. So now I have to round this to 3 sig figs. No leading zero is important. I'm reading it like I'm reading a book, and I'm blasting on through anything that is not a digit 1 through 9, right? So zeros get out of here. My first significant digit is 4. So I have 4, and then I want the 3, and then I do want that 7, but he becomes an 8 because the 5 is telling me to round him up. So that's my answer, and I'm excited about that. But what are the units for this answer? Oh, no one can know. Well, it's specific heat, so you can either memorize, well, specific heat's units are joules per grams degrees Celsius, or you can look at the dang units that you've put into your substitution. I have a joules up on top. I have a grams down on bottom. I have a degrees Celsius on bottom. Wow, that looks like joules. And then grams, degrees Celsius. Joules and grams, degrees Celsius. Perfect. So that's the specific heat of, what was this about? Nickel. It's a very low specific heat. We said waters is 4.184. That just lets me know that low specific heat. It doesn't take a lot of time or energy or heat to heat up the temperature of that nickel. So that's very exciting. We get it. You guys, Q equals MCAT. The only thing a little bit hairy and weird is just keeping aware that the subtraction step to find that delta T, the result of that step is what I'm going to be looking for sig figs for rounding purposes when I do eventually solve for whatever they're asking me to solve for. Okay, so let's bounce back to our lesson because now we're going to extend this Q equals MCAT in some way. Okay, so now we have done a lot of fun things like talk about Q and heat and our heat being released and absorbed, and talk about delta H and heat being released and absorbed, and she's using the same terms like negative is release and positive is absorb and endo and exo and all that fun stuff. You're like, well, what even is the difference between Q and delta H, or the change in enthalpy? Y'all, it's not much, really, and a lot of times both terms can kind of be used somewhat interchangeably because both do represent heat energy that's either released or absorbed. Delta H for the reaction, since it's for a reaction, is used specifically for chemical reactions. And Q can be used for all chemical and physical processes. It can be used just to heat up a sample of matter, not forcing it to undergo a chemical reaction or a chemical change. They are kind of the same thing as long as they're under constant pressure. And y'all, since most reactions occur under constant pressure, we're like not in outer space or in the bottom of the ocean, we can kind of say that these two things are equal, okay? The theme here is when Q is positive, energy is absorbed. That process is an endothermic process. When Q is negative, energy is released, and that's an exothermic process. So good, they kind of mean the same thing. I don't know why there's 2 letters of the alphabet. That's kind of inconvenient, but it is fine. We can roll with it. All right, now let's extend this into a lesson on calorimetry. Okay, so we know that all chemical processes involve absorbing or releasing heat, meaning they are either endothermic or exothermic. But how can we measure how much heat is absorbed or released in a chemical reaction? If I am doing the formation of water from hydrogen and oxygen, I cannot stick my thermometer into the reaction system, into the atoms themselves, and like measure the temperature change. Like I do not have the ability to do that. Okay, so we have to kind of measure it indirectly, and we measure it indirectly using a process called calorimetry. So calorimetry is a method used to determine the heat that's involved in a physical or a chemical change. It relies on the law of conservation of energy. So a calorimeter is a little cute little cup and insulated device that it's used to measure the amount of heat lost or gained by a chemical reaction, or even sometimes a physical process, okay? It works by measuring the temperature change in the water surrounding it. So a calorimeter is basically like a cup of water that's sealed off as much as it can, where you can place a vessel of a reaction down in there, or you can drop a sample into there. And we are assuming that if that reaction releases heat energy, it will be absorbed by the water, which I can measure how the water is changing its temperature, or it can be absorbed by the water, or that water will release its heat energy into the reaction system. Either way, I can measure a temperature of the water change. So looking at this, we are assuming, due to the law of conservation of energy, that the heat absorbed by the water in the calorimeter should be equal numerically to the heat that's lost from the sample. Okay, I'm going to get back to this equation. I want to talk about what we're seeing right here in these pictures. This is a very simple diagram of a calorimeter. Basically, I got some water in here, and y'all, I got a thermometer so I can measure the temperature of the water. Boom! Before I did anything and put anything inside that water, it was 58 degrees Celsius. Sounds good. That's an initial temperature, huh? Now it looks like I've dropped a metal sample into that water. It was apparently hot because heat is being released from the metal into the water. And we know that heat is always transferred from the hotter thing to the colder thing. But look at this. As a result, the temperature in the water went up a little bit. Well, that makes sense. If the water is absorbing that heat energy, it would increase its temperature. So I'm not able to directly measure how much heat that metal is giving off. But because of the law of conservation of energy, I can see, oh, how is water experiencing this energy transfer? And then I can calculate the heat for the metal sample. So since the metal is releasing energy and the water is absorbing that energy, I can say that their two Q values, or their two heat transfer values, are going to be the same. But one is releasing it, so it will be negative, and one is absorbing it, so it will be positive. Okay, so heat is being released by the sample into the water, and therefore the temperature of the water will rise. If heat is being absorbed by the sample from the water, then we would expect for the temperature of the water to raise. So we can do this with our Q equals MCAT equations. Okay, so here's another nice picture of a calorimeter. Here's my reaction vessel. It looks like that heat is being transferred from the reaction into the water, meaning it is being released, right? Okay, so we can say that heat released by the sample, if it's being released, it's going to be a negative Q. And that heat is going to be absorbed by the water in the sample. So that water will have a positive Q. Their Q's will be the same. So yeah, here it is. The equation is stating just that, right? The Q of the water will be equal to the opposite sign, or the negative sign of the Q of that sample. Okay, we know Q is equal to MCAT, so this is equal to MCAT, and this is equal to MCAT. But those M's, CP's, and delta T's on this water side, all of those values need to represent the water and not the sample. Versus over here, the M, the CP, and delta T needs to represent the sample. Okay, we're going to watch a quick video on this calorimetry, kind of a little bit more explanation on it, and then we're going to see how we can implement this and do some math problems.
In this video, we are going to learn about calorimeters, what they are, how they might be used, and why they are used. A calorimeter is a device used for calorimetry, the process of measuring the change in heat of chemical reactions, or physical changes, as well as heat capacity for a material. When you look at food items, their energy content was worked out by burning the food in oxygen to see how much energy is released. This corresponds to the energy content label and is given in calories. To do this, you have to use a calorimeter. The simplest calorimeter consists of a thermometer attached to a metal container full of water and is suspended above a combustion chamber. In a typical calorimetry experiment, you can measure the energy that is released from fuels. Can you think why this might be important? The answer is that different fuels release different amounts of energy. So if you're flying a plane, you need a fuel which releases more energy than, say, if you were driving a car. This is because the plane is heavier than the car, so more energy is needed to make it move. In the classroom, if you do this experiment, you would do it on a much smaller scale, using a spirit burner. This is what you would need to do. 1. You'd measure the mass of the spirit burner before the experiment. 2. Add a certain amount of cold water into a copper calorimeter, a small metal can, and suspend it at a fixed distance from the spirit burner. Can you think why it is important for it not to be too far away? Pause the video and continue when ready. The answer is that in this sort of experiment, a lot of the heat is transferred to the surroundings, so you need to minimize this by either placing the spirit burner as close to the calorimeter as possible, or you could reduce this by insulating the sides and adding a lid. 3. You'd measure the starting temperature of the cold water. 4. You'd use the spirit burner to heat the water for a fixed amount of time. 5. Record the mass of the burner afterwards so that you could calculate the mass of the fuel combusted. And finally 6. Record the temperature change of the water caused by heating. Can you think why you might do the experiment more than once? Pause the video and continue when ready. The correct answer is that you want your results to be as accurate as possible. This also improves the reliability of the results you collect. If you have a larger temperature change on doing this experiment with one type of fuel than another, this means that more heat energy was transferred to the water than if you have a smaller temperature change. The best fuel is likely to release more energy per gram of fuel. In summary, calorimeters are devices that can measure the heat of chemical reactions, physical changes, or heat capacities for different materials. A simple experiment showed how measuring the temperature change of water could be used for this purpose. The larger the temperature change per gram of fuel, the more energy released.
So calorimetry relies on the law of conservation of energy. And you guys, this is how for all food we've measured how much energy content or how many calories a piece of food has by putting it in a calorimeter and burning it and seeing how much energy is released from that food item and taken into the water. Our bodies actually have a whole bunch of little combustion reactions of our food particles where we actually get that heat energy from them, but it's at a little teeny tiny scale to where we don't feel like we're burning things in our body. That was a tangent. But let's do some practice problems with this because this is a real fun concept and I'm actually super excited. Okay. So down here, and once again, we have our equations stated. I typically do not mess with this interpretation of the equation. I think about it more as you're going to solve for the Q of either the water or solve for the Q of the sample, and then whatever the opposite sign is of that, that will represent the Q for the other guy. Okay, there's no way I can handle that many letters of the alphabet or numbers plugging into stuff. So my thinking here, and I think that this may be helpful, is solve for the substance. And when I say substance, I mean either the water from the calorimeter or the sample. Solve for the substance that you have the most variables for. So we're going to say solve for the guy that you know the most about. Okay, meaning the guy that I have all of the information about as opposed to the other one, because you're going to see lots of numbers in these problems. You're going to see a couple of masses. You may see several temperatures, but you're going to zone in and try to pick out, well, who's got all of the things that I need to solve for a Q value. You solve for that first. So y'all aren't ready for all the numbers in this problem here. Are we ready? Okay, it says when a 200-gram block of iron is placed in 1,500 grams of water at 25 degrees Celsius, the temperature of the iron decreases from 160 degrees Celsius to 110 degrees Celsius. The specific heat of the iron Oh boy, it's fine. We're going to look at these numbers. We're going to look at the units and we're going to identify if they are M, T, CP, whatever. So my first value here is a 200 gram. Gram. Y'all, that is a mass. Block of iron is placed into 1,500 grams. Uh-oh, that's another mass. Y'all, we got two guys here happening in here. One represents the mass of iron, and this represents the mass of the water. We stated that each part of this calorimetry experiment has two mass values. Well, there they are right here. Now we have to figure out which one has all of the values that we need, whether it's the iron or the water. So let's see what other values we get. So that's 1,500 gram sample of water is at 25 degrees Celsius. So that's my initial temperature for the water. And if you want, you can kind of ID who these things belong to. It's a little bit more writing. You definitely don't have to do it, but if you get like overwhelmed, oh, that's not for the water. I got in the group, started writing H2O for everything. And so this is iron. I'm gonna write Fe because it's less letters of the alphabet than that. And it's also the chemical symbol for iron, so we love that. So the temperature of the iron decreases from, so this is my initial temperature for my iron, to that. Boom. So that's my final temperature for my iron. The specific heat of iron is 0.450 joules per grams degrees Celsius. So that's my CP of the iron. Okay, before they even ask us to calculate things, they're just saying this. If it is run under perfect conditions, what can we assume? You were like, I do not. What do you mean? What can we assume? Well, first of all, the law of conservation energy is going to be preserved here. We are assuming that the energy transfer will be complete, meaning whoever is releasing energy, the other guy will absorbing that full energy. Now, the next question I do want to ask you, though, is who is transferring energy to who? Is the iron transferring it to the water, or is the water transferring it to the iron? Well, how am I possibly to know? Well, look at their starting initial temperatures. We've already identified them. Iron's initial temperature is hotter than water's. So if you want, you can, I like to sometimes even draw. Here's a little calorimeter. Yes, here's my sample of iron. According to their initial temperatures, he was hot when I dropped him in. We know heat transfers from the hot thing to the cold thing. So now I can visualize that iron is releasing heat to the water. So I can make this statement: the Q of the water will be equal to the negative Q of the iron. That means the iron is releasing heat energy, a negative, and the water is absorbing that heat energy, so it will be positive. The numbers will be the same, just the opposite sides. Okay, so we're going to say heat is completely transferred from the iron to the water. Okay, so we can make this statement, which says that heat will be completely transferred, because those Q's are the same, from the iron, who is a negative, to the water, being the positive. Okay, so now let's get ready to do some math here. How much heat, which is Q, is lost by the iron? Well, it makes sense that they're saying lost, because we've already established that. Isn't that amazing? So we can say heat is what we're solving for, and because we know that heat is lost, we're expecting to get a negative Q from this calculation. Okay, so let's go ahead and establish Q is equal to MCAP, but we are going to specify that this is Q of my iron. So we are solving for the Q of the iron, which means I make sure that I put the mass of the iron, the specific heat of the iron, and the temperature change of the iron. Do ignore all of the water values up here. Okay, so I have, for my substitution, did we find the mass of the iron? Yep, it was 200 grams. And look at all those zeros. I bet you those zeros are going to be important for sig figs. They are. Specific heat for the iron. Did we get that? Yep. 0.450 joules per grams degrees Celsius. And then finally, my temperature change. Temperature is always final minus initial. For the iron, though, what was the final temperature of the iron? 160. Is there a decimal at the very end? Yes, there is. oh, I didn't need to close parentheses, minus the initial temperature of the iron we said was, oh wait, no, that's not my final. Sorry guys, this is my final temperature of my iron. It was 110 with a decimal there at the end, minus 160 degrees Celsius, okay? Now, as we mentioned, we got to be heads up on these sig figs, right? Ooh, heads up on the sig figs. So if I wanted to real quick in my calculator do 100 minus, or 110 minus 160, 110 minus 160. Yes, you get a negative temperature change. That is okay. We're going to roll with it. And in fact, that negative temperature change may have some impact on whether I get a positive or a negative Q or heat. So I have negative 50. Now, that decimal at the end tells me that those two zeros that are in the ones places for those two temperatures are significant, and I need to keep that place value represented, so I had to put a decimal here at the end. So looking at this guy, I've got a 2 sig fig situation. Yep. Okay, so now we're going to do the math part. We're going to do 200 times 0.450 times negative 50, and we get this number. Okay, we were expecting to get a negative number. We know that the iron was releasing heat energy, so I got a negative Q. That sounds good to me. Okay, so we're going to say Q of the iron is equal to sig figs of it all. Okay, well, this guy has 4 sig figs. I don't look at specific heat. It's a constant or infinitely significant. And that one we said has 2 sig figs. So we would need to round this answer to 2 sig figs. It is already represented in 2 sig figs. So we get excited about that. So I can say negative 4,500. And the units for Q are joules. Okay. Now, since the question said how much is lost by the iron, it's understood that we're going to be answering this question of giving you a value of heat released. But I always like to put the negative there anyway, because follow-up question is going to ask us some questions about the water, and we know that this sign change is going to be important for us. So the next question is what is the temperature change, or the delta T, is what we're solving for here in the water. Okay, well, how am I supposed to know that? Well, we got some real important information from this. If we know the Q of the iron is negative 4,500 joules, well, guess what the Q of the water is? It's the same number, but positive. So we can say the Q of the iron equals negative 4,500 joules. Therefore, the Q of the water is equal to positive 4,500 joules. Yes, this is the whole essence of calorimetry, this complete transfer of heat energy due to the law of conservation energy. Okay, so now to solve for the temperature change in the water, I get to use another Q equals MCAT equation, but this time where all of the values are represented by water. So we can kind of state that off. Since we're going to have to solve for delta T, we're going to have to move our equation around. So I'm going to actually write my Q equals MCAT as it was normal, and then isolate my delta T variable. So the way that I would isolate the delta T variable is his sneaky buddies of mass and specific heat go to the bottom of the other side. So the Q of the water divided by mass and specific heat. Okay, amazing. So do we have the Q of the water? Yes, it is the positive version of that, which you do not have to write the positive sign. The absence of a positive sign is still understood that it will be positive. So then we got to get to the mass. Did we have the mass of the water in this problem? We did. 1,500 grams. Noticing that decimal, that's important. And then finally, do we know the specific heat of the water? Water's specific heat is always 4.184. 4.184 joules per grams degrees Celsius. Amazing. Okay, so now we are ready to calculate. I don't have a temperature change to do some subtraction for first because that's what I'm solving for. So then we go, let's say, we go 4,500 divided by 1,500 and then also divided by 4.184. And we get this number. Okay, this number is very exciting for us. Let's see now. How many sig figs? Let's see. So this guy has 2 sig figs. And this guy has 4 sig figs. Yes? So I'm looking at this, I need to round it to 2 sig figs, right? I ignore the specific heat. He's a constant. He's infinitely significant. So 2 sig figs for this would be 0.72. And this is a specific heat value. So according to the units that I've written in my equation, I'm going to make sure that I put in those units for specific heat as joules per grams degrees Celsius. Awesome. So joules per grams degrees Celsius. Very exciting. So what we've kind of done here is we have looked at the fact that when I have a calorimetry set up, energy is going to be completely transferred from one thing to another. So due to the differences in temperature, the hotter thing will transfer the heat energy to the other thing. So it will release heat energy, a negative Q, an exothermic process. And the other thing that started at a lower temperature will absorb the heat energy, a positive Q, an endothermic process. But this all relies on the law of conservation of energy. Technically, to have a perfect calorimetry experiment, it needs to be a completely closed off system that's insulated to where you're not going to accidentally release heat to the surroundings.